Three, two, one. Exciting. All right, let's go. All right. Pre-recorded in-person live lecture. Very exciting. Okay. All right, so, last time we got determinants set up, and now we want to use them. How do we use them? And the main use, so as I mentioned in the video, the multiplicative property of determinants is, quote, the most important thing, as per Dr. Weber's opinion on it. And so we want to kind of see why that ends up being true, right? Or why he thinks it's a very important fact. Because it is. It's insanely important. But why it's insanely important, like I mentioned, there's kind of this special linear group stuff that it's kind of connected to, but for a bit more practical for us, a big use of that fact is when it comes to eigenvalues. Right. So you have potentially encountered the exciting world of eigenvalues before this class. If you're taking differential equations, you got a big old dose of it. But through mathematical cultural osmosis, you've possibly ran into these. All right, so here's what we're going to do. We're going to start with eigenvalues as broadly defined as possible, and then we will hone in on a specific case. So what I mean by that is we'll look at eigenvalues for linear operators, and then we'll bring it down to matrices. All right, so again, we know that matrices give us linear mappings, but linear mappings kind of go beyond matrices. So a good place to start with eigenvalues is linear transforms. All right, so specifically, given a linear operator from a vector space to itself. So again, remember, the phrase linear operator is reserved for a linear mapping whose domain and codomain are the same set. We'll go ahead and say that a scalar, and right now we'll say it's in the reals, but it's very possible that what we're dealing with is a what happened there? It's supposed to have a fancy C showing up, but for some reason it does not exist. Now it does. All right, so generally speaking, we'll stick to reals, but it is worth noting that things are going to go complex. This is one of the reasons we needed complex numbers, because as we're going to see, computing eigenvalues ends up being related to getting the roots of a polynomial. The roots of a polynomial, we know, potentially involve complex numbers. All right, so we'll say a scalar, real or complex, we'll specify if it has to be complex, is an eigenvalue if there is a, and we want to stress something here, a non-zero element of our vector space such that the linear operator's action on this thing, and let's actually use u for that instead of x, so that when I feed that into my linear operator, I just get that scalar multiple of u, sorry. Okay, all right, so let's break this down. Okay, so again, a eigenvalue is a scalar so that there is at least one non-zero vector u, so that the action of t on the vector is to just scale it. So our linear operator, right, which will take our elements in a vector space V and move them to a vector space V and do it respecting scaling and adding, the action of this is to just leave it alone and hit it with a scalar. All right, so the word eigen is the mathematical equivalent of the word quantum, in the sense that people just throw it in front of things, and here you go. The only funny part of Ant-Man and the Wasp, you guys just put the word quantum in front of it. I laughed super hard at that, because I was like, yeah, it's the same thing as eigen. It wasn't the actual joke. It was like a completely different thing, made me laugh. But anyway, so eigen is a loan word from German. It means same or self, depending on kind of the context. But note, that's what effectively it's saying. This is a scalar, so that the linear operator, right, gives you the same thing when you input u, but it's not necessarily exactly u, it's some multiple of u. So, hence the name. All right. And before we go any further, I bolded the word non-zero, and I really want to note that. Note that since recall that any linear operator, any linear mapping, sends 0 to 0. Let me rephrase this. Note the non-zero requirement is because we know any linear transform sends 0 to 0. So if I did not require non-zero there, then everything would be an eigenvalue. Because scaling the zero vector gives you the zero vector. So if you do not require the existence of a non-zero vector u satisfying that equation, well, then everything's an eigenvalue. So it's not a definition. That's garbage. Cool. All right. So now that we have the appropriate definition of an eigenvalue, all right, we've got it there. We can start digging into it and figuring it out. But let's get some examples first. So let's begin with some basic examples. All right. So primarily, we are going to be interested in the situation of matrices. However, we've defined these for linear operators. So we'll get a traditional example of matrices, and then we'll look at some more fun ones with linear operators. All right. So let's start off with a matrix example. Let's do so let's create this matrix right here, this matrix 1, 4. Very exciting. All right. I claim that lambda equals 1 is an eigenvalue. Now, if you've got some experience with eigenvalues before, you hopefully can look at this matrix and immediately tell me the eigenvalues are 1 and 4. Those are the two options. What was that noise? Anyway, but if you don't, right, don't worry, we'll get to it. But anyway, I claim that this is indeed an eigenvalue. Now, in order to do that, I need to explain to you why there is a non-zero u, so that when I apply u to the linear transform here, now remember, if you have a matrix, the linear transform is matrix multiplication. What is the vector u that's going to work here? Well, this one, there's kind of a cheapo answer. Because if I let the vector u be the standard unit vector 1, 0, well, what happens when I look at a times u? All right, well, multiplying by a standard unit vector will isolate the associated column, and lo and behold, the first column of that matrix is the standard unit vector itself, so I just get back 1 scaling u. So in particular, right, here we see an eigenvalue of value 1 would be there is a vector that is a fixed point of the mapping. So there is a vector that when you apply the mapping, it does not do anything, it remains fixed. Nice. Note further, and this will be something we'll explore a little bit further. There is nothing particularly special about the vector u here, right? I just need a 1 there, so that when the multiplication happens, I get this. But note, I could replace that with any value I want. All right, so if I were to look at the vector v, where v just has some alpha up there, I don't care what that is. If I do the matrix multiplication for this, so if I look at a times this vector, note that you'll just get that vector back. So there's actually nothing special about this vector u we found. In fact, any vector, as long as you've got something up there, is going to work. Now note, alpha could equal 0. Note the requirement for it to be an eigenvalue is there is at least one non-zero thing, but sort of as we already pointed out, 0 always works too. Right, so we found a specific non-zero u, but then kind of looking at it, we realized any scalar multiple of that will also work. So once you have your eigenvalue, note that the associated vector that you're looking for, there's actually more than one possibility. In fact, there's infinitely many. In fact, there might be like, oh, I don't know, a whole subspace associated with that. That was on an exam review. I didn't put it on the actual exam, but it was on the exam review. All right, cool. All right, so there we go. So now we got an example of one. Pretty cool. Let's now, so the matrix example, let's look at a more interesting vector space example. Let's do a specific operator example. All right, and I'm going to need to introduce some notation for this one, but we'll go ahead and let all right, so I'm going to let C infinity 0, 1 denote the set of infinitely differentiable functions on 0, 1. Now, we talked about C0, 1 before. That's the set of continuous functions. And you can start putting things up here with the C to indicate how many continuous derivatives you've got. All right, and C infinity is you have infinitely many derivatives, right? So differentiable, let me spell that correctly. All right. So, for example, of things that live in C infinity, like e to the x, it's its own derivative, and so you can take the derivative infinitely many times. Cosine and sine have a similar thing. Polynomials have infinitely many derivatives, and all of our usual kind of favorite functions, when well defined, will have infinitely many derivatives. Power functions, for example, that'll be all good. Cool. All right, so that's what that notation means. So if you've seen it before, great. If you haven't, you will. All right, well, something we've mentioned before is that there are linear transforms that you've encountered in your math life before you got here, and maybe even explicitly said, hey, I'm looking at a linear mapping, or this is the linearity of, for example, differentiation. Derivative is a linear operation, right? You scale a differentiable function, you get the scaled derivative. Take the derivative of the sum, you get the sum of the derivatives. Hey, there you go. All right, derivatives behave linearly. All right, and I need an operator, which is why I'm focusing on C infinity, so the mapping goes from C infinity to itself. Obviously, if you're infinitely differentiable and you take the derivative, you're still infinitely differentiable. You haven't taken any more derivatives. All right, now note here, what would an eigenvalue for this be? An eigenvalue for this mapping would satisfy what? Well, I would be able to find, and we'll use an H for this. Right, if we just write out the definition, this says give me a function and take its derivative. Well, an eigenvalue would satisfy that t of h has to equal lambda h for some non-zero infinitely differentiable function. However, the action of t is to take the derivative, and oh hey, we get a first order differential equation. In fact, we get the first order differential equation. Find me a function whose derivative is a scalar multiple of itself. So note, if we were then to define the function, let's use g here so we're not kind of overloading. The function g, that's just e to the lambda t, take its derivative. By chain rule, the lambda jumps out, but then you still have e to the lambda t, so this satisfies it. So in other words, and note e to the lambda t is obviously a non-zero function. So in other words, what we have here now is a linear operator that has every scalar as an eigenvalue. So differentiation is a linear operator, and it literally has every possible eigenvalue it could have. Every real number counts as an eigenvalue for this thing. Pretty wild. Yeah.
We only need to find one function such as g
Yes.
to be able to.
Yeah. Yeah, you only need, there is at least one. And obviously, if you know your differential equations, you'll get, if you wanted to solve that DE, you would get all scalar multiples of that singular function. Right? But to verify you are an eigenvalue, you need just one non-zero thing to work. You can then figure out everything that works, but in order to get the actual value part, you just need to find one non-zero thing. Right? We'll talk about getting all of them for matrices specifically. All right, so we had our matrix example, and like I said, if you've encountered this before, you already know that this matrix has precisely two eigenvalues, 1 and 4. And in a little bit, we'll justify that for matrices, they'll only have finitely many eigenvalues ever. All right, now we have a linear operator from our differential equation or calculus days that we know this linear operator has infinitely many eigenvalues. Pretty cool. Let's flip it. Can we create a linear operator that has no eigenvalues? Interesting question. Now, there is a way to sort of cheese this with matrices, depending on your viewpoint, because as we will discover, there are real matrices of real entries, that have complex eigenvalues. So some people would be like, well, the matrix was real, so the complex eigenvalues don't really count. So some people would argue that that doesn't truly have any eigenvalues, even though it does, but yeah, you have to make the jump from the reals to the complexes in order for that to be true. All right, well, those naysayers, I'm going to give you one. It's possible to create a linear operator that truly has no eigenvalues. And this is, I love this example. I hope you love this example as much as I do. This example is so cool. All right, so we introduced C infinity, the set of infinitely differentiable functions. Now, again, note that is a vector space because it's closed under scaling and adding. And let's recall that when we were talking about this stuff, I pointed out my particular favorite vector space is C01. This is the set of continuous functions that are defined on the interval 0, 1. C01 is one of the coolest goddamn things ever. I love this vector space. It has all sorts of cool properties. And I've spent a lot of time just hanging out here. It's awesome. It's my favorite. This is my math home, if I'm going to have one. When I go into my math brain, this is where I live. I love C01. All right, and what I really love about C01 is that it's got a lot of really neat properties, but also has a lot of misbehaviors that are worth mentioning. And one of them is that there's a linear operator you can create that doesn't have any eigenvalues. So we're going to define our linear operator as follows. Okay. Now, here's where we're going to have some notational pain that we're going to have to deal with. So note here, recall, this is functions. So a function input and a function output. All right, I'm going to do the same thing. I'm going to say, give me a continuous function, turn it into this one. But notatively, it's going to be a bit of an overload. So at first, it's going to be a little tricky to kind of look at, but it's not that bad. Okay. So if I input a function f, I get an output function, capital T of f. Now, if I want to make a function, I need to tell you its output for an input. So what I've written here is that the output of the function t of f at the input little t. All right, so visually it's a little weird at first, but let me write out what it does. It takes your function, evaluates it at t, and then multiplies it by t. All right, so at first it looks a little like, okay, what the hell is this? But let's plug in a couple of functions so we get a feel for what it's like really doing. So this is sort of a notational thing you got to deal with. Given a function that has function input and function output, you can evaluate that function then at some inputs, but so then you get this sort of weird notational thing. So some people will really overload the parentheses here and will do that. So it's really clear what's going on. Some people just don't give a shit and go, okay, TF of T like this, where you're like meant to understand what's going on, right? It's, you put F into T and then you evaluate it at T. So they'll drop the parentheses. And then there are the absolute fucking lunatics that will write this. Because it's like the ordering of how you apply things. You apply capital T first to F, and then you apply little t for the input. And you read it from right to left, because like math operations, like that's kind of how you apply them. It's like reading like a composition of functions. You don't really read from the outside in, you read from the inside out. So some people will write it like this. And those people, these are grade A lunatics that write it like that. But I was trained by my advisor to write it like this, so that's what we'll write. But let me get some examples here so you get an idea of what it really is doing. All right, so let's pop in some functions. So for example, if I just plug in the function x, note that you would get x squared. Right, because it would be your function times the input. Well, right, x is give me input, leave it alone. So if I plug it in, it multiplies by itself and gives me x squared. All right, let's get a couple more. So we're really good with it. What happens if you do plug in e to the x? All right, well, it just multiplies it by x, right? You take your function and then multiply it by the input. And finally, for example, if you were to plug in sine, you get x sine of x. So this mapping here takes a function and then multiplies it by its input. All right, so that's the action of the mapping T. Okay, so you can verify that T is linear. It's not too hard to verify that it is indeed linear, right? Because if you feed in a linear combo, this T multiplying here is just going to distribute across. So you'll just get appropriate scaled and added outputs. What I really want to point out is that this function can't possibly have eigenvalues. Right, because if it did have an eigenvalue, that would mean that we can find a non-zero continuous function that would satisfy the following equation. For all t in 0, 1. Right. So, if t had an eigenvalue, lambda, there is a non-zero function so that t of g is equal to lambda times g. But my action of my mapping is to multiply the function by the input. And now, sort of, you can immediately see this can't possibly be true, right? There is no function so that scaling it is the same thing as multiplying by its input. If the function is continuous, so we need to be a little careful. So at first glance, that equation seems like, yeah, there's no way that's true. Let's actually work out the details as to why. That's spam. I don't need to answer that. Actually, should have mentioned, if my phone goes off, I might have to actually answer it. That one I don't. That one's spam. Something about my loan's been approved, so I better hand over my social security number and my bank account and your blood type and how many kidneys do you currently have. All right. Anyway, okay. So, by assumption, there is a non-zero, there is an input. Right, so we've assumed g is is a non-zero function, so there's some point where it's not equal to 0. And now if I plug that into my equation up there, and activate the math lizard brain, and subtract it over, right, so subtract this over, right, we know there's an x where g of x is non-zero, all right, well, you can then factor out your g of x, and since this is non-zero, it's got to be that this quantity right here is 0. All right, so our function g is non-zero, which means its output is not equal to 0 somewhere, and we've just verified that that output has to actually be that input actually has to be the eigenvalue. All right. All right. However, if we apply the same sort of logic now, pick a input t not equal to the eigenvalue. We then have the following, next page. Following the same argument, we would then have this. And now, if t is not the eigenvalue, now note the eigenvalue is the point where the function is not equal to 0, this then would force g of t to equal 0. Because the t minus lambda there, note, is non-zero, because t is not equal to lambda. So what have we just proven? Well, my function g now has to be the following piecewise function. I've just proven that my function does the following. At t equals lambda, it just outputs whatever g of lambda was. And, I didn't spell lambda right. And I didn't end my cases, so it's really yelling at me. All right. And then for any input that's not lambda, this function equals 0. So I have a function that everywhere is equal to 0, except at the point t equals lambda, that's non-zero. Right, this isn't continuous. Which would get us a contradiction. So this linear operator cannot possibly have eigenvalues. Even if you were to allow for complex ones, even if you were to go nuts and be like, well, okay, you're allowed to play in complex numbers, still doesn't work, right? It didn't need to be a real scalar. You could go nuts. You can make them quaternions, make them octonians, like go wild. All right, cool. So this linear operator here truly has no eigenvalues. Cool. Pretty neat. Love this example. Right. Again, I love it for messing around with continuous functions. My favorite vector space of all time. My favorite place to hang out. Yeah, good stuff. All right. So there we go. We've gotten a sampling of eigenvalues for general linear operators. Let's now go ahead and discuss and prove some basic facts about such things. And the big one is the following. Right. Nope. All right. So, given a linear operator and an eigenvalue, we'll define E sub lambda to be the set of vectors that satisfy the characteristic equation. The T of V is equal to lambda V. This is called the eigenspace, and the elements are called eigenvalues, eigenvectors. Right. Now, it's called eigenspace because, note, we've already proven that thing is a subspace. We did it for matrices in the exam review, but if you replace the matrix multiplication with linear operator, it's the same proof, and you will get that this is indeed a subspace. And in fact, furthermore, it's non-trivial since there has to be at least one non-zero element that lives in it. So you have a non-trivial subspace here, and so you know it's got to have at least dimension 1, and computing the dimension of this thing is something that is very interesting. For matrices, the dimension of this thing is called the geometric multiplicity of the eigenvalue lambda, and we'll talk more about that next time. But something I want to prove about the eigenspace, this will be our proof for the day, is the following. All right. Yep. What's it yelling at me about? Oh, where is... Oh, my God. Hold the fort. That's right. Okay. All right. All right, it's good now. There we go. All right. Now actually the proposition. Okay, so we're going to prove the following. If you've got a linear operator and lambda is an eigenvalue, we know that the image of a subspace would give you a subspace. And so an interesting thing is to look at, well, what's the image of your eigenspace? And here we see that the eigenspace's image remains in the eigenspace. And the proof here is pretty quick and easy. I'm just proving subset in one direction. So let's go ahead and pick a element y that lives in the image of the eigenspace. All right, well then y has to be t of v for some v in the eigenspace. All right. Now I want y to be in the eigenspace. So in order for that to be true, I need to see what t of y is doing. Yep. And what do I want? Well, I want t of y to be lambda of y. All right, well, let's look at what t of y should equal. Well, t of y would be t of v, like that. Next, just what is y? It's t of v. But we know about v lives in the eigenspace, which means that t of v is actually lambda v. All right, and what do we know about t? We know t is linear, so that lambda can be pulled out. And what do we know about t of v, though? T of v is equal to y. And there we go. Y lives in the eigenspace. Pretty neat. And let's wrap up today with a fun, unsolved math problem. So, in light of this proposition right here, that the image of your eigenspace remains in your eigenspace, the eigenspace is given a fancy name. It's called an invariant subspace of T. It's a subspace that when you apply T to it, it doesn't go anywhere. It just hangs out in the subspace. It's invariant under its action, hence its name. Invariant was one of my advisor's favorite word to use to signal that you were doing real mathematics. All right, he was like, use the word invariant. Sounds like you're doing more than you really are, which is just, I'm looking at things that when you apply the function, nothing happens. Don't say that. Say that it's invariant under its action. Now it's, ooh, now you're doing something. Even though it's like, what are inputs that don't do anything interesting? All right. So, and I'll put this in bold, invariant subspace problem is basically, given a linear operator, does it have a invariant subspace? Now, if you have an eigenvalue, the answer is yes, because your eigenspaces are automatically going to be invariant subspaces. So you're looking for subspaces where the image stays in the subspace, and you want the subspace to be non-trivial, because obviously the trivial subspace doesn't do anything when you feed it into the mapping, because you just send 0 to 0, so obviously it's invariant. That's not interesting. So find me, if I have a linear operator, find me a subspace, not trivial, so that feeding it into the mapping doesn't do anything. So the question is, can you always do this? Given any linear operator, must it have an invariant subspace, yes or no? So if it does, great. Now note, for eigenvalues, if they exist, the answer is yes. So what we're going to discover is that for finite dimensional vector spaces, the answer to the invariant subspace problem is always yes. Every linear operator will have invariant subspaces, because every linear operator in finite dimensional vector spaces will have a matrix, and thus it's got eigenvalues. Again, as long as you allow for complex things, and this problem is always stated for complexes because of that. So the interesting thing is what happens when you're infinite dimensional. Well, we just demonstrated a linear mapping that doesn't have any eigenvalues, but that doesn't mean it doesn't have invariant subspaces. It just means that, well, if there is an invariant subspace, it's not going to be coming from eigenvalues, it has to come from something else. So the problem is super interesting when you're infinite dimensional, and it's been studied to death. And for the longest time, people were suspecting the answer was yes, you always have invariant subspaces, as long as you were looking at nice linear operators defined on nice vector spaces. But then, in the 70s, a guy named Per Enflo actually showed the answer is no, you can create bad linear operators on nice vector spaces. Nice enough vector spaces, anyway. And so the parameters of the problem got changed over time, and right now, the current problem is continuous linear operator on a separable Hilbert space. So in that situation, everyone suspects the invariant subspace problem is true, but nobody's been able to prove it, and it's been unsolved for like almost 100 years now. And Per Enflo, speaking of him, was the one who originally took it down in the 70s. He has posted a couple of papers claiming that he's finally figured it out for separable Hilbert spaces, but he's in his 80s. What?
Doesn't have a space to write it.
No. It's like 11 pages. But he's in his 80s, and he kind of showed up out of nowhere with this, and everybody's very suspicious about it. And right now, the prevailing thought is, so he did this about 2 years ago, where he just jumped out of nowhere and said, hey, I finally solved it. And it's been 2 years, and at this point, everyone's pretty sure what he has isn't actually correct. But he's like the one dude with enough clout to have like kind of showed up and been like, yo, I did it. And everyone like, oh, you probably did it. But from what I've gathered, so he posted one paper, and he posted a like updated version of it that supposedly fixed an issue. But by the sounds of it, it's still unsolved. So the invariant subspace problem is still up for grabs as far as I know. Per Enflo probably did not solve it, but I don't know. Not clear. But anyway, so there you go. Good stuff. All right, so what's the plot for next time? So we've introduced eigenvalues for linear operators. Next time, we will focus specifically on the matrix case and really dig into that and see what's going on there. So, all right, there's your broad overview of what eigenvalues and eigenvectors are. Next time, we'll focus in on the matrix case and really talk about what happens there. All right, that's it for today.